partially destroyed. And Theia, which had an iron mantle, lost its iron mantle to the Earth. The iron part of it went into the center of the Earth, so now we've got an Earth with a great big huge iron center, which is good for reasons I'll explain in a sec. So we've got the Earth with a great big huge iron center, and a lot of the volatiles, those are elements up at the top of the periodic table. I want to show them the periodic table for a sec, number 40. The elements up at the top of the periodic table, the light elements are the ones that boil off easy, and the ones down here, the heavier elements, don't. So we've got a hot moon right next to a hot Earth. The Earth is thousands of degrees, and the moon, instead of being 384,400 kilometers away like it is now, was only about 25,000 kilometers away. So the moon was picking up all this heat from the Earth. Because the Earth is big and the moon is small, the Earth captured the moon in its gravity and tidally locked it, probably almost right away. So now you've got the Earth turning slowly and the moon turning faster, but they're both turning at such a ratio that the same side of the moon is always facing the Earth. So the moon is turning. It never has not turned, and it will continue turning even as it gradually moves away from the Earth, which it is doing at the rate of 3.78 centimeters a year. So eventually the moon will be a much longer way away, but right now we don't have to worry about it. And the fact that we've got a moon there is a really important thing, because having a moon there stabilizes the Earth. It stops it from tilting all over the place. The interplay of gravity between the moon and the Earth keeps the Earth stable. So that, you remember last time we were talking about Milankovitch cycles?
Yes.
Give me something here, folks. Tell me you remember something about Milankovitch cycles. Well, if you don't, you're asking for it, because I'll tell you all over again. So, come on. If you were a class, I'd test you. You guys wouldn't be getting away from this for 1 second. Really, all I want is to feel you're going away having learned something. You just take as much as you want. Anyway, what happened was this guy called Milutin Milankovitch, a Serbian mathematician, was looking to find out a reason why we had ice ages. And he concocted a theory whereby ice ages are caused by three things: the Earth's orbit, the Earth's wobble, and the Earth's tilt. In terms of its orbit, the Earth goes around in an almost circle, but not quite. And if the circle is perfectly circular, it has a different influence on how much radiation from the sun the Earth can pick up. So that's one of the three factors. The orbit. Is it circular or is it a little bit egg-shaped? Egg-shaped means elliptical is egg-shaped, okay? So here we got Milutin Milankovitch. Here we've got the Earth. And what we're looking at here in the middle is something called, it's called the precession of the equinox. This thing we've got here is not entirely accurate. And I'm telling you, you've got to really be careful with AI if you're trying to use it. Because I was trying to find out what exactly the influence of the Earth's wobble was. You see, Milankovitch said, okay, you've got an orbit that is either circular or almost circular. You've got a wobble too, because what happens, the Earth is like a spinning top. When you spin a top, you can see that it wobbles, right? Well, that's what happens to the Earth. The Earth has been spinning ever since it got created, and especially ever since it got hit by the moon. That started them both really spinning, and that probably put the Earth on the angle that it is now. The angle varies from 22.1 to
24.5.
Yeah, 24.5. That's really good, man. You're smart. And that wobble has an effect on when the seasons occur. But the biggest of the three, out of orbit, wobble, and tilt, is the tilt. The tilt varies from what, 22.1 to 24.5, right? And the tilt is actually called the precession of the equinox, not axial precession. But I'm telling you, you've got to watch it when you look stuff up. The irony is, it's like in the old days when we used a dictionary. You're looking up a word you don't know how to spell. Okay, that didn't go over too well. But anyway, carrying on. Milankovitch then said these three things are why ice ages occur. And he said the biggest reason why ice ages occur is because of the tilt. What the tilt does is determine how much radiation, solar radiation, you get from the sun in the summer or the winter. And the important thing is, if the summers, what brings on an ice age is not cold winters, it's cool summers. Summers where the ice doesn't melt. The snow that falls doesn't melt. So one year the snow falls and doesn't melt. The next year it falls and doesn't, not all of it, right? Over a few millennia, a few thousand years, you've got it converted to ice. Each layer compresses the layer beneath it, and you've got ice. And eventually, what happens is something called a tipping point. I was going to deal with it down here, and I'll deal with it again. I'm not proud. A tipping point is that at that point after which things are irreversible. And what happens in an ice age is, now, we need that one of those ones with the earth half ice at the top, ice all over the earth. Okay, hon, I don't know. I just want a picture of the earth covered with ice. Oh, thank you. All right, so here's how it starts. The ice starts at the poles. If it continues to build up because the summers are cool and it's not melting, it starts to move down and up, right? Because this is the warm part and this is the cool part. And when it gets to a certain point, and that point is 35 degrees north or south, when it gets to a certain point, you can't stop it. Because what's happening is that ice has what is called an albedo. Everything has an albedo. That's the amount of light that it can reflect. So if you're standing on an asphalt road, that's not very bright, right? Okay. You know the moon's not there? That's got exactly the albedo of asphalt. And yet it still manages to shine that brightly, which I think is really quite something. So let's hear it for the sun. Anyway, once it gets down past 35, you can't stop it. Because at that point, it's reflecting so much light that it just keeps getting colder and colder. You got it? Now, what's happening or what happens is, see those oceans? Those are dark. Those soak up energy. And matter of fact, let me show you where things get soaked up. Let's have number 20. I think that's James Clerk Maxwell and the electromagnetic spectrum. Okay. There's your electromagnetic spectrum. This part you can hear. This part you can cook with. This part you can't see, but man, is it important. This part we can't see either, but bugs can. And if you look at your average flower out there, try to imagine as you're looking at it that flower very likely has patterns on it, which function as landing instructions for insects, because the flowers want to be pollinated, right? So they do a couple of things to get themselves pollinated. One thing they'll do is put a nice pattern there. You know, some flowers have got a dark middle. You know why that dark middle is? It soaks up heat because it's dark. It soaks up 6 times as much heat as the light part of the petals. And a flower that's got a dark middle like that can get 6 times as many bugs on it as a flower that doesn't. So sometimes we can't even see that because the patterns are in the ultraviolet. Anyway, this part up here is the part that'll kill you if you're not careful. Gamma rays will destroy your tissue. They ionize your tissue. They lock the electrons off of atoms and cause them to disintegrate, and that creates radicals, and it's just a mess. X-rays, gamma rays, ultraviolet. So a lot of birds and bugs see in the ultraviolet. Now, the infrared. All right, there is this word called carbon. A lot of people don't like it because they think it's a political word, but it is not. And so I'm just telling you straight out that I organized these lectures to be about science. And science is what it's going to be about. And the science is the science says that what carbon does, carbon dioxide specific, is it soaks up heat in the infrared. Okay, what happens is electromagnetic radiation comes from the sun. So it comes down and it hits the earth. Some of it gets reflected. If you've got a lot of ice, you're going to get a lot of it reflected. If you don't have much ice, it will get absorbed, right? So dark surfaces soak up light. What I'm seeing here is this coffee cup, which is greedily soaked up every single photon within sight, and I'm seeing black. If it was giving all the photons off, I'd see white. And that's how color works. When you're looking at color,
You want it back?
You're looking at wavelengths. Here I went to dramatically illustrate the Maxwell equation, or the electromagnetic spectrum. So, carbon dioxide then traps, you've got this incoming radiation, comes into the atmosphere, and about half of it gets deflected back out, depending on, as I say, what the albedo is, right? What was that?
Do you want the albedo again?
No, I didn't want albedo. Oh, but the infrared. So the light's coming down, it's getting deflected back out, but some of it doesn't get back out, which is where CO2 comes in. CO2 traps it in the infrared part of the spectrum. And that trapping in the infrared part of the spectrum is what causes the planet to get hotter or colder. So we'll be looking at life on Earth, and life on Earth is inextricably tied up with the surrounding environment. That's what Charles Darwin's Origin of Species is all about. Darwin didn't invent evolution. Evolution's as old as the hills. The ancient Greeks thought about it. Anybody looks at anything and you can see things change. You have to mental giant to see that, right? The point is, how do they change? How do things change and yet stay the same? Life changes, and yet life is always similar to the life that's gone on before. And no two things on Earth that are alive today are identical to the kinds of things that were alive on Earth 252 million years ago when we had the worst extinction of all time. 96% of everything, all life on Earth, became extinct. Why was that? Because there was too much carbon dioxide in the atmosphere. There was an area over in what is now Russia called the Siberian Traps, and that whole area erupted. That is a big area. It is about as big as Canada. So we had an area erupting 255 million years ago on a scale that none of us could even imagine. And what happens is, when you've got volcanic eruptions like that, you have the completion of what is called the carbon cycle. And so I'm just going to reinforce something with plate tectonics. We've done Milankovitch. I think we're through. But just remember this, the Milankovitch cycles say that you'll get an ice age under certain conditions, but those certain conditions always include the level of CO2 in the atmosphere. Let me tell you something else about carbon. The word organic, everybody knows the word organic, right? It's a beautiful word. It always, no matter what it means to you, it's nice. You know, it's organic. It's got to be good.
It's
right?
healthy, eh?
Okay. But organic is such a widely used phrase that it basically means nothing, right? So here's what it's going to mean to us from now on. Organic means carbon. So if you go to university and you want to be a biologist like I did, you're going to have to take organic chemistry. I didn't. Organic chemistry is viewed with loathing and horror by all students who have to become biologists. It's just this awful thing they've got to go through. Because organic chemistry is all about carbon. It's all about how carbon bonds with carbon and about a million other things. So organic in chemistry means of or relating to carbon, because carbon is the molecule which, more than anything else, all life depends on. If you had to choose one atom out of the entire periodic table, number 40.
Oops, sorry. Sorry,
That's
press the
Charlie
wrong.
Chaplin and Einstein.
I'm really.
I got to tell you a story because you weren't here, I don't think. You know, Einstein, right? I mean, everybody knows Einstein. Charlie Chaplin was one of the most famous entertainers in the world. He was a mime. He did his entertainment without speaking. Remember The Little Tramp? Have you ever seen any Charlie Chaplin stuff? Anyway, I really liked him myself, and so did Albert Einstein. He was Albert Einstein's famous star. Anyway, they finally met, and Einstein says to Chaplin, he says, "I really admire your work." He said, "Somehow you managed to create a universal language where even if you don't say anything, everybody knows exactly what you mean." And Chaplin said, "Thank you, but yours is the greater glory." He said, "Nobody understands what you mean, but they love you anyway." So, that's the periodic table. I had it up there for some reason.
You're talking about carbon.
Carbon.
Organic
Yeah.
chemistry.
Yeah. So, thank you, dear. Organic chemistry is about carbon and everything that it bonds with. So, you hear people say things like, well, you know, if life came from somewhere else, we'd know it because probably be made out of different stuff. And so would the spaceship and everything else, right? They come from a different part of the universe, different. But no, as a matter of fact, everything in the universe that can be is on the periodic table, at least according to the chemists whose lectures I've listened to. They keep insisting on that again and again. And the best lecture I ever listened to was on the periodic table. I mean, can you imagine anything more boring, right? So I'm sitting there, it's a university lecture, right? So I'm going to sit there for about an hour. I listened to a lot of these things the last few years. This guy comes out, he's the most boring looking guy in the world, right? His hair's a bit rumpled, his tie isn't tied quite right. Got a suit on, it's not good, not bad, you know. You know, can you imagine, a bit of a paunch, not much, kind of rumply looking guy comes out and he proceeds to talk about the periodic table and the invention of everything in the universe and how the elements came to be, and he shows you pictures of supernovas happening. It is the best freaking lecture. If you get a chance to view it, the guy's name is Ed Murphy, and it's the periodic table. And it's the most boring thing you could think of, but when you watch it, you realize here is a master. This is the guy I want to be, totally in control of his material, knowing it so well that he can present it in such a clear, vivid, entertaining way that you learn as you go and you just love it. So, The Periodic Table by Ed Murphy, ladies and gentlemen. Not the world's most boring lecture. At any rate, carbon is what it's all about. Why carbon? Because carbon can bond with a whole bunch of other things, so it's really good at creating chemical bonds, but the bonds are not too stable. They're stable, but not too stable. And see, if you're going to have an element that you're going to build life around, it's got to be stable, and yet it's got to also be flexible and reactive, because all metabolism involves chemical reactions, and you can't live without metabolism. How many cells do we have in our body that are metabolizing right now? That's a question that you can answer, because I've already told you. Each lecture, I told you.
I know.
Not that I would want you to feel guilty.
I know.
Okay, baby. I mean, Denise. Go ahead.
I might be wrong. 37 million?
37, the number 37 is correct.
Billion?
Yep.
Billion.
37.2 trillion cells.
Trillion.
Trillion in each human body on average. Molly wouldn't have quite as many because she's not quite as big. Women and children have numbers in the high 20s or low 30s. Don't feel bad. Your mom's got a full complement. You will too.
How many would I have then?
Sorry?
How many would I have then? If I don't have many?
Probably around 20 trillion, 25 trillion, somewhere around there. But my point, Molly, is that in every one of those cells, in every second, there's all these chemical reactions going on that keep us alive. So we've got 37.2 trillion cells with about 1 billion reactions going on every second. So that's 37.2 trillion times 1 billion. That's the number of reactions that are going on in here in my body. Well, maybe a few fewer in yours, but you'll pass me, trust me. Anyway, that's what's going on right now, and that's all revolving around carbon, because carbon can make those connections and break those connections at just the right rate, right? So stable, you got to be stable, but you also got to be flexible. You can't survive on Earth if you're not, because everybody's got DNA, and your DNA is a certain way, and there's the environment, and your DNA, that's you, and the environment have got to get matched up. That's what evolution is all about. So if you and the environment are matched up, then you're adapted, and you're doing great. But if they're not, you're maladapted, and I'm sorry, but you have to go extinct. That's just the way it is. Really sorry to tell you that, ma'am, but so that's how it works, and it works around carbon. Carbon is the central atom. You might think, well, come on, what about oxygen? Because after all, we live in an oxygenic world, right? We've only lived in an oxygenic world for 500 million years. Before that, there was no oxygen floating around in the atmosphere. None. It was a foreign atmosphere. If you'd been on this Earth 4 billion years ago, you couldn't have breathed the atmosphere for 1 sec. They're not sure what it was. They think it was mostly CO2, some nitrogen, a bit of hydrochloric acid, a bit of hydrogen. It's a horrible place, right? It's not fit for man or beast, literally. None of the things that are on the face of the earth right now could survive, except for a very few that are living in weird places, like at the bottom of the ocean, around hydrothermal vents, in hot springs at Yellowstone, in caves under the ocean, or they found life over 12 kilometers below the surface of the ocean. Now, there's a whole subterranean world now that's just starting to be discovered. Speaking of something else, well, so much to tell you. That's the point. And it's so hard to keep track of it all. That's why I rely on Denise.
Do you want to show Alvin? Not right now?
Well, at some point I do, yeah.
Okay.
Let me just finish about carbon, because that ties
Yeah.
in with the carbon cycle
Sure.
and with tectonics.
Sure.
And then we'll do the other thing, okay?
Okay.
So, basically, let's look at a cutaway of the Earth. Can we do
Okay,
that? I
yeah.
can't remember what number it is.
88 is the big one.
Okay. You remember this from last time, but just to reinforce this, okay? We're up here on the surface. Down here is a solid core. And this core is solid because there's too much pressure down there for it to be anything else other than solid. It would like to be a liquid, and this part's a liquid, but this part is too scrunched to be a liquid, so it's forced to be a solid. We're really lucky that that part there is liquid. Why? Anybody? Ferris Bueller's Day Off. Gotta love it.
Anybody?
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 Anybody? If you were a class.
Oh.
Anyway, this part is liquid, and the reason that's a good thing is because it sloshes around. As the Earth turns, this liquid kind of sloshes around, and that sloshing makes it a dynamo. And the dynamo means electricity, electromagnetism, thanks to James Clerk Maxwell and his 4 equations, which came out in 1865.
I think I know where they are. Hang on.
It's okay.
No, I got the
That's
wrong
Newton,
one.
but-
I got the wrong one. I was close though.
Newton's cool. Newton's totally cool.
Eric got it.
I just discovered something. I want to emphasize that. I'm a learner. Like, I'm with you guys. I'm a student. I'm learning stuff every day. So I just can't wait to get here and tell you about everything I learned. I was just reading about structural coloration. Everything has a color. That color is a result of what wavelengths are being given off. Everything has its own unique signature of wavelengths. And I also knew that color was created in 2 ways. One way is by pigment. Plants invented a pigment called chlorophyll by which they can convert photons into chemical energy. There's all sorts of chemicals out there that are pigments, and so they make most of the color. But some color is created through reflection and refraction. So if you look at a peacock's tail, that peacock's tail is actually brown.
Wow.
But it looks blue and violet and all these gorgeous colors because the light is coming in. The peacock's feathers are arranged in such a way that they've got these little flat things called lenses. And they're arranged in such a way that light comes in and it either reflects, bounces back off, or it refracts, goes through and bends. And when it does those 2 things, the angles that it makes between the light going this way and that way create the colors that you see coming off the peacock feathers. So it's just a dull brown feather. But thanks to the way the molecular arrangement of those sheets, the light is reflected, and refracted in such a way as that we see all those gorgeous peacock feather colors. Terry knows them better than most because he spends his time harassing those poor trout. And peacock feathers are big in fly tying. I used to have them all over the place. So I was big into peacock feathers. But sorry, Terry, I didn't realize you were there. I wouldn't have embarrassed you like that.
I fell asleep for a minute.
So yeah, I know peacock. And guess who it was that figured out how that works? It was Isaac Newton, and that's what reminds
Isaac
me of it.
Newton.
No, and him.
Okay.
Not him, no, Thomas Young.
Yeah. Okay.
So it was Newton and Young. Young was the guy who figured out light was a wave. He came up with this double slit experiment, which is just plain weird. So there he is, the last man who knew everything. That was his title. 1801, he proved that light was a wave. And he also, building on the work of Isaac Newton, proved what I just told you, that structural coloration is caused by the mechanism I just described. See how everything fits? I just learned that last night over a few brownies. Anyway, where are we? Okay, Now, oh yeah, now I get to tell you about ringwoodite. This is, oh, I don't know, this is cool. But first, let's go back to our cutaway of the
Yeah.
earth, just to make sure everybody understands. This is super important. So you've got this sloshy area down here, the outer core, and that's what's giving us the electromagnetic field. Why do we care about that? Because the sun is trying to fry us. The sun has UV, you've probably heard of it. It's that purple area in the electromagnetic spectrum I just showed you. That UV can be really hard on you. It's very harmful. So that sloshing of the core creates the magnetic field. We actually have a picture.
Can I show that?
Yeah, sure, show them a magnetic field. Let's live dangerously. Oh, there it is. So out at the bottom and at the top, there's your magnetic field. And that is protecting us because the sun, let's say the sun out there, So the sun is, let's see, 149.86 kilometers away. It's firing all these, all this solar, it's called a solar wind. The solar wind is hitting us and it's spreading out around what is called the magnetosphere here, and that's kind of tailing out in that direction. So it's coming from the sun, hitting this, and then kind of tailing out. And that is protecting us from the sun and allowing life to live. Otherwise, it would be destroying our DNA every second, and we would not be able to live or reproduce. And reproduction is one of the key elements of life. So, going back to our cutaway again. Funny how you just showing that picture of Newton just reminded me, right? Anyway, here's another cool thing. I might have told you this, but maybe I didn't. It's 6,371 kilometers from Merritt to the center of the Earth. Okay? And if you subtract 2,900 from it, which is the size of the core, so you go down 2,900, you hit the core. You go down 6,731, I think it is, and you hit this. If you take that away from that, you end up with 3, 4, 7, I think it's either 2 or 3. And the reason I mention that is because that is exactly the size of the moon. We have, within the Earth, I noticed that one day. I started doing the math. I thought, can this be right? So I looked it up, and sure enough, it is. There's only 3 or 4 kilometers difference between the size of the moon and the size of the center of the Earth. So just imagine we got this little moon down there underneath our feet all the time. That's so cool. And there's a lot, the reason there's so much iron down there is because we got it from Theia, when Theia hit us 4.51 billion years ago. Isn't that cool? So now, back to our, oh yeah, and the idea being, looking at our cutaway again, if we could, huh? The idea again being that, again, plate tectonics, there's your ocean, there's the underneath, there's your ocean, there's your land. The bottom of the ocean is this thin strip of crust. And the bottom of the ocean, the crust, is made out of metal that is called mafic, which means it's got a lot of magnesium and iron in it. Now, the general term we use for metals that are dark, dense, and metallic, and have a lot of magnesium and an iron, is we call them mafic rocks, and the best known mafic rock is basalt. I'm sure everyone has heard of basalt. So what happens is the bottom of the ocean is made of basalt. Let us look at that one where we can actually see the subduction occurring.
Absolutely, yeah.
So the bottom of the ocean is a thin, dark, dense crust, and the crust over the land is lighter and floats. This is mostly granite, which is a felsic rock. I introduced these terms to you last week. I'm going over them again. Mafic means metal, and it stands specifically for magnesium and iron. And the reason it stands for iron is that the Latin word for iron is ferrum. By the way, Latin was what the Romans spoke. Those guys,
Yeah.
they built those great roads, and they had this empire. So the Romans spoke Latin, and the Latin word for iron is ferrum. So whenever we refer to iron, we call it either ferrous or ferric, and that will apply directly to the first life on Earth. We're going to have to deal with the words ferrous and ferric, because the first life on Earth, we think, if that life up in Nuvunatuck, if that turns out to actually be the earliest life on Earth,
Yeah.
then that earliest life on Earth made its living, stayed alive by being able to convert ferrous iron which is dissolved iron, into ferric iron, which is undissolved iron. That life form would have taken the electrons. I've harped a lot about electrons, right? Okay, so that primitive life form that existed 4.28 billion years ago, when the Earth had only been around for 300 million years, that primitive life form, isn't that? That's what it was, stayed alive by converting dissolved iron, ferrous iron, into ferric iron by removing an electron. That changes the iron into a different kind of iron. And the difference is, if you've got a glass full of water with ferrous iron in it, the water will be clear. But if it's got ferric iron in it, it'll have this goopy, orangey, browny, pinky kind of sludge. And that is what's left behind by these bacteria when they convert iron from one form into another. So they convert it into another form, it comes out of solution, and whammo, you've got goop all over your plumbing appliances or your kitchen or whatever. I was carefully cultivating a little bit of goop in the kitchen, right where the spout comes up. There's a backsplash back there. Where the counter meets the backsplash, I noticed there was this little bit of pinky material, right? I thought, oh, this is great. That means there's iron bacteria in there, and they're converting the ferrous to ferric iron. And this pink goop we see is what's left behind. Then Denise came along and destroyed it. I hate it when people come along with these household. Anyway, but we don't know for sure. And I am jumping a little ahead of myself, but yeah, there's this place up in East Shore, Quebec, and right now there's a lot of activity up there because the word got out that the oldest rocks on the Earth were up there. And then the word got out in 2017 that they think wedged in the cracks between those rocks, they found this early life form. And then they revisited some guys from McGill. In 2019, they wrote another paper on it because they'd received a lot of criticism. People were saying, well, that could have been formed abiotically, that is, not by life. So these guys went back and they did a more thorough thing and they found some more fossils and they wrote up another paper and they're doubling down. They're insisting this is the oldest life on Earth. So right at the moment it's up in the air, but the oldest life on the Earth could be up in the Canadian Arctic. And even if that is not the oldest rock, there's another rock up in the Canadian Arctic over to the west and up further north called the Acasta gneiss. Gneiss is a type of rock, Gneiss. And the Acasta gneiss has been dated at 4.01 billion years old. So either way, Canada, baby, oldest rocks in the world. Before that, you would have had to go to Australia or Greenland, but we've taken over from Greenland and Australia. All right, looking at that cutaway.
Cut it back
again.
to the cutaway.
And then at the one.
Oh, yeah.
Yeah, I want to imagine people, we're going to go down the I-5, and we're going to imagine what plate tectonics have done to the scenery as we're on our way down. Right?
Absolutely.
There it is. Yeah, okay, okay. So let us imagine that we've gone down to San Francisco and we're heading back, and we're coming up the I-5. Most people have been on the I-5, right? So you're driving along on the I-5. Over on your left is the ocean, except you can't see it because there's a row of hills between you and the ocean. And over to your right, when you get to a certain area, you get up high, and then you see these beautiful, great big huge volcanoes like Mount Shasta now, right? All these gorgeous volcanoes, some of which are not by any means extinct. Matter of fact, some of them were only made 4 or 5 million years ago, so they're not all that old. So it's pretty recent. Anyway, you're driving back, and you're driving up this big central valley. There's an ocean over there. There's a row of hills between you and the ocean. You're in a valley, and there's these big, beautiful mountains, raising their lofty snow-capped peaks to the gorgeous blue sky, which 4 billion years ago was not blue. It was this horrible sort of orangey pink color because it was all carbon dioxide and methane and stuff like that. We would have gone, fallen over dead immediately. Well, we've done it before that because there was 27 atmospheres worth of pressure, and at one point it was 280 degrees Celsius, so that's pretty warm. It would have been a hard place to be back then. But life started. This is the thing. Anyway, this is subduction. The oceanic crust, which is thin and old and cold, meets the continental crust. Well, 3 things can happen. Well, no, two things can happen, basically. One is, one can go that way, and the other can go that way. And if that happens, you've got the San Andreas Fault situation, where you've got two continental plates locked, and they're each trying to go the opposite direction. And they build up pressure, they build it up and build it up. Finally, it gives, and you get an earthquake like the one in 1906 in San Francisco. They've had other ones since then. So here we are on our I-5, and we're coming back, and this on our left is where the ocean, the oceanic plate has subducted under the North American plate. And as it subducts, as it goes down, it takes the rock with it. And as the rock goes down, it gets hotter and hotter, but it doesn't melt because there's too much pressure. But then what happens is it takes water down with it. And the water hits a certain depth. And that depth is often around 660 kilometers down, at which point the water melts. Or the water acts as a flux, like when you're soldering, and it causes the magma, the rock down here, to melt. And the melted rock then, because it's hot, so the melted rock is now trying to find its way up, just like all things do when they get hot. They want to rise, right? So the magma starts to rise up through the mantle, and then eventually makes its way through the crust up here and comes out as a volcano. So what's happening is two important things. Number one, all the rock in the world is being recycled. That's why there's almost no really old rock, because it's been being recycled. Well, they're still arguing about when the recycling started, but I'm going to assume, actually, I'm going to go with what I think the majority opinion is tending towards, and it looks like it's tending toward the idea that plate tectonics started early. So we're going to assume that plate tectonics started by 4 billion years ago, and what it did was it started taking the rock and the carbon, remember, in the rock, down with it. When the rock gets to a certain depth, the water causes the rock to melt. The melt rises as magma, and if it can find a way through, it'll come out as volcanoes, and that's what created those beautiful big mountains that you see over to your right if you're coming back, or over to your left as you're going down. And all the mountains, Mount Meager, Mount Baker, Mount Shasta, Mount Rainier, all those lovely volcanic peaks were all created by magmatic activity over the last, I think it started 13 million years ago, and had different, I mean, I don't know a lot about that particular period because I've been concentrating on earlier periods in the Earth's history, but that's the basic idea, which I've got right. And so that's how those mountains are formed. And what you've got is you've got the ocean, it's always the oceanic plates, and this subduction is recycling all the rock, and it's also recycling the carbon, and that's the important part. Plate tectonics, this is the message I'm trying to get across. Now I'm going to give you a break. Plate tectonics are the means by which the planet controls its temperature over long periods of time. That's how it does it. It takes carbon, like what happens is you've got the air. Let's say it rains. Okay, raindrop comes down and it goes through the atmosphere and it meets carbon dioxide in the atmosphere. The carbon dioxide gets in the water and forms a very mild carbonic acid. So each raindrop is like a little tiny carbonic acid bath, right? And it's just very slightly acidic. You wouldn't notice it if you drank it. It's very slightly acidic. Gets down, hits the ground, soaks into the ground, reacts with calcium carbonate, which is limestone. Limestone is made by little sea creatures that take calcium out of the water, incorporate it into their shells. And so that's what clams and oysters and things like that do. Okay, so the carbon comes down, gets into the ground, gets into the rivers, and gets washed down into the ocean. When it gets to the ocean, all these little sea creatures grab it and start making houses out of it. But eventually they die, and so their little bodies sink into the bottom of the ocean. And over hundreds and thousands and millions, a couple of million years, they get all compacted down there, and then they end up getting subducted down into the ground. And what comes up out of the volcanoes is carbon dioxide. There's a number of other gases come out too. If you get a lot of sulfur dioxide coming out, it can actually cool things down for a bit. But mostly what has happened, nearly all volcanic eruptions, and all volcanic eruptions eventually, spew out carbon dioxide. So carbon dioxide is in the atmosphere, gets washed out by the rain, into the ground, down the oceans, down the rivers, to the ocean, to the bottom of the ocean, then subducted from the bottom of the ocean down, comes back up as magma, and comes out as carbon dioxide and forms new rock. So the youngest rock in the world is on the bottom of the oceans, and the oldest rock is on the land, because the oldest rock on land is felsic, which is light rock made out of silicon and feldspar, and the other kind on the bottom of the ocean is mafic, and it's made out of magnesium and iron. Magnesium and iron are heavy, silicon and feldspar are light, and so these light-colored rocks, there's the Acasta gneiss that I was telling you about. So that's a rock that probably started out igneous, then it became sedimentary. The igneous rock broke down into little bits. That became sedimentary, sand, mud, silt. That got compressed down into the earth. When you mash something down, it gets hot, and so it gets hot and it metamorphizes. It metamorphizes and becomes, so it turns from its original thing into something else. And this has ended up as gneiss. So it started out as some kind of sediment, igneous rock, then it becomes sedimentary. Then the sedimentary gets recycled, subjected to heat, and it gets altered, and it finally ends up, it goes into schist, and then it gets altered into gneiss. This is a piece of gneiss, except it started out as a more mafic rock with more metal, and that's why it's darker. Okay, let's continue on after a quick break, okay? Thanks very much. We're going to start by looking deep down in the earth. I talked about 660 kilometers down. I didn't just choose that as an arbitrary figure, but there's an area down there, 660 kilometers down. Okay, we want the cutaway of the earth. We want the cutaway
the
of the
big
earth.
one? That one?
Yeah.
Okay.
So if we go down, let me just grab my trusty thing here. 660 kilometers. That'd be embarrassing if I missed. We come to what is called the mantle transition zone. And down there is a substance called ringwoodite. It's a type of rock.
Cool.
Yeah, and nobody had ever seen ringwoodite ever up until a few years ago. But all scientific theories make predictions, and if it's a good scientific theory, the predictions will eventually be seen to come true. And that was the case with ringwoodite. They were sure that it must exist, but 660 kilometers is a long way down underneath the ocean, so you can't go down there to check it out. So nobody had ever seen ringwoodite. Then somebody was examining a diamond from deep underground in Brazil, and in the diamond they found a tiny little bit of ringwoodite. It was microscopic. It's not much bigger than a bacterium, but there's a bit of ringwoodite in there, and it was just like they thought it would be. Ringwoodite, well, you know that all chemicals have a structure. All chemicals have, like a chemical like water is hydrogen, 2 hydrogens, and 1 oxygen. Okay, so that's one of your simplest chemicals. Ringwoodite is put together, so all chemicals are put together having a formula, like H2O, or, I don't know, let's pick another formula. Let me just write it on the board. I've always wanted to write a formula on the board. Let's try CaSiO, and we'll throw in some aluminum, and we'll call this a 2, and that a 2, and that's an 8, and that's called anorthosite, and that is a type of felsic rock which comprises the crust on the far side of the moon. That's what the far side is made of. On the top, the near side, on the top, is mostly basalt. So they're 2 totally different kind of rocks. Now, the thing with ringwoodite is, like all chemicals, it's not only a mixture of different things. Let me think. Ringwoodite is, I'm just showing off now, I admit it. MgSiO4. That's what ringwoodite is. Everything down there is that. That is basically olivine, which is that gem known as what, peridot or something like peridot or something like that. It's this olive green gem. Well, that's a mixture of magnesium and silicon and oxygen, with maybe a bit of iron thrown in. So if I was going to get really fancy, I'd throw a bracket and say it was Fe, but I'm too lazy to get up. So that's a chemical formula. My point here is that all chemicals have a shape. They have a structure. They have a 3D structure. And ringwoodite has a 3D structure that allows it to trap water, except that it can't trap water in the liquid form. The water has to be split up so that it becomes a hydroxyl or a hydroxide. That's an OH. So it's really simple stuff, really, honest to God. You take water, that's H2O, 2 hydrogens, 1 oxygen. Just take 1 hydrogen out, you got HO, or it's often expressed OH. And that's a hydroxide. It has a form called hydroxyl too, and that is what ringwoodite has got a structure that allows it to trap water in the hydroxide form in itself. And they figure, they, being scientists, that there's between 1 and 3 oceans worth of water in that ringwoodite 660 kilometers down. Just think of the implications of that. 3 oceans worth of water stored away in the ringwoodite. It's not, I had a hell of a time getting my head around this. I mean, I even wrote to Louis Zucchetto, head of the physics department, hoping he could explain it to me, right? Because whenever I think of water, I think of a liquid. It's hard for me not to think of water as a liquid. But this water is in there in a hydroxide form. It's not a liquid, it's not a gas, and it's not a solid. It's in some kind of in-between state. And if it's going to become liquid water, then you're going to have to reunite it with an oxygen. But there's oxygen everywhere, so that's not a problem. But most of the oxygen, that is up until recently, up until 500 million years ago, all the oxygen on the face of the, well, no, up until 2.5 billion years ago, but basically 500 million years ago, almost all the oxygen was locked up in rocks, like there, magnesium, silicon, and oxygen. Do you know that the biggest part of rocks is oxygen? Do you ever looked at a rock and thought, hi, oxygen? But that rock has more oxygen in it than anything else. It's got more oxygen than iron or calcium or sodium or even silicon. The second biggest thing is silicon. But it's got more oxygen than anything else. So just, that's what I'm trying to get my head around with this chemistry thing, right? The bugbear of my existence. You know, I'm just looking forward with horror to having to explain anything to do with chemistry. Brings back these hideous memories of me at SFU in that chemistry lab and all these people in the white coats walking around with beakers. And I'm sitting there thinking, I'm really a fish out of water here, right? I don't have a clue what's going on. And all these other people are writing up equations and they got their little beakers and everything, and I'm out of it, eh? But I'll tell you one thing. The science department had the best Christmas parties that were ever invented, because they had this alcohol. And I used to play up at SFU, so I used to get invited to all the parties, and I was on the students' council too. So, and I'm telling you, I was at parties with the dean. You get invited to all these big shot things, but the best parties were the science labs. They had these great big jars, inverted jars, and with a valve at the bottom. And one said, I don't know, innocent punch or something like that. Then another one was like regular alcohol. Then there was another one that was stronger, and then there was another one that had like pure lab alcohol, which apparently is 99 point something, but can't quite be 100% alcohol. I had to explain, but of course I didn't understand it, but it's as close to 100% alcohol as you could get. And man, those were really good parties. They really rocked, I'm telling you. So all I can say, if you ever meet a science denier, I've been there, I've been in those labs. Those people were my friends. This is real stuff going on, real science, and real alcohol, believe it. So that's ringwoodite. So down there is this ringwoodite, and this ringwoodite has in itself 1 to 3 oceans worth of water in a non-liquid form. And what is being hypothesized then, to bring this to a close, is that functions as part of a huge water cycle in Earth. So that on Earth you've got the oceans. Just see how small the ocean is if you compare it to and that's not even to scale. Okay, to scale, those globes that everybody used to have in school? I thought they were the coolest thing. Eh? They had you could run your hand over it, and you had all these mountain ranges. You see where the Himalayas were and the Rockies. Well, you know what? If that were really to scale, if that globe were really that big, and you ran your hand over it, you wouldn't feel a thing. You wouldn't feel a thing. Tallest mountain on Earth is Mount Everest, 8,848.84 kilometers high. That's 29,031 feet. That's Mount Everest. That's as far as anything goes. And if that were to scale, you wouldn't even feel it, because the Earth is pretty big. The Earth is 12,756 kilometers if you measure it through the middle. If you measure it through the middle, I'm not talking about circumference, I'm talking about diameter. Measure through the middle, it's 3,756. If you measure it from top to bottom, it's 12,722, I think. Anyway, I did the difference, and there's a difference of 50 or so kilometers, depending. Why am I talking about that? It's not
I
even
don't
important.
know.
Okay, sorry. I just thought it was interesting. Anyway, so, hell, what was I talking about?
You were finishing off with ringwoodite, darling. There's
Okay.
1, 3.
Thanks.
Now the water.
Okay, you've got the ringwoodite. It's got all this non-liquid water stored in it. There's the ocean up top. My point was that compared with the size of the Earth, the mountains are nothing. Mount Everest at 29,000 feet is nothing when you consider that the diameter of the Earth is 12,756 kilometers if you measure it through the waist. That's all. That's the only point I was trying to make. We covered your basic rocks, ringwoodite. Just a little, Molly, I got to tell you, last time I mentioned something I thought was really interesting. This. Have you ever addressed what this is?
Yeah, our nictitating membrane.
This is the Plaquia semilunaris. And what this is the remnant of when we had a third eyelid. And we, along with various reptiles, mammals, and other creatures, had at one point, when we were back evolving from fish, we had a nictitating membrane that would function as a third eyelid and close the entire eye. Now, I pointed out last time that animals like falcons still have them, and they use these nictitating membranes as little windshield wipers to keep their eyes clear as they're diving down after the pigeons. The most thriving population of peregrine falcons in the world lives in big cities, and they live on pigeons. So that it's perfect. It's perfect. Falcons almost became extinct because DDT was killing off all the large raptorial birds in North America, like eagles. I remember back in the 1970s, there were only about 400 eagles left in the United States. There was a bunch up in Alaska, but in the continental, they were almost gone. And so they banned DDT because DDT caused a chemical reaction in the birds, which meant that when they laid their eggs, the DDT interfered with the shell forming of the eggs. It interfered with the ability of the eggs to metabolize calcium into the shell structure. And so when those falcons or eagles laid their eggs and sat on them, they just went like that. And that's why they were becoming extinct. So they banned DDT. And when they did, the birds started to come back. And the falcons, which were almost extinct all over the world, BC, Canada, proved to be a key area where people came and were given special permission to get falcon eggs and take them all over the world and hatch them and try to bring back the peregrine falcon population. And one place where the peregrine falcon population came back really well was in New York City. So you've got all the skyscrapers. What is a falcon like? A falcon lives on cliff faces and way up trees and stuff like that. Nothing could be better for falcons than all these great big huge skyscrapers. Plus the fact that people brought pigeons over. Those pigeons are not native to North America has many native pigeon species. It had one called the passenger pigeon. Have you heard of them?
Yep.
The passenger pigeons were the most numerous bird in the world. There were literally billions of them. They literally covered the skies when they flew over. People writing back in the 1800s talked about how when a flock of passenger pigeons went over, it darkened the sky for 3 days. That's how numerous they were. Now, there are none. We killed them all. The last one, named Martha, died in a zoo in 1929. That was the last passenger pigeon in the world, if you can believe that. Anyway, I think I mentioned that in regards to peregrine falcons, because there are no more passenger pigeons, but there's a ton of other pigeons, European pigeons. They're called rock doves. They're the ones you all know. And they're the ones that pigeon fanciers work with. And they were a huge influence on Charles Darwin when he was formulating his theory of natural selection. Because he looked at artificial selection and thought, same thing's going to work in nature. Just got to figure out how nature does it. Anyway, so that's your nictitating membrane. Those are peregrine falcons. Peregrine falcons have made a huge comeback. And they're big in New York. They're flying all over the place in New York. I just love it. Eh? There's these pigeons down there, and all of a sudden, New York City, out of the sky, 320 kilometers an hour, passenger pigeon, the fastest thing in the world, hits the pigeon. There's a ball of feathers. Oh, it's just great. Anyway, I just love seeing things like that come back. That's what a nictitating membrane used to do. All right, so we finished all that. Done albedo. So the point with the albedo that I wanted to stress was that once something like ice gets a hold, it reflects so much stuff that pretty soon it can't help but reflect so much stuff that the temperature goes down. So the carbon and the carbon cycle is the way that the planet Earth has regulated its temperature ever since the beginning. It takes a few million years for it to work because the carbon has to be taken out of the atmosphere, into the ground, down to the ocean, buried in the ocean, turned into rock. Well, first it has to be made into little shells by sea creatures, and then it gets turned into rock, and then it gets buried, and then it heats up, and then it melts, and then it comes up as carbon dioxide. So that's the carbon dioxide cycle. And they think, because of the presence of woodite down there, that there's also an ocean cycle, and that the ocean gets recycled on a long-term but regular basis. Water goes down, water eventually comes back up. Where does it come back up? Let's have a look at those mid-ocean ridges, can we? I can't remember what the number is offhand.
Do you want the actual picture of the? I've got this one here. There you go. I got this one here, and I also have. Oh yeah, this will be the one.
Okay, so yeah. Except I wanted a map too to show where they were. But in the middle of the Atlantic Ocean is the Mid-Atlantic Ridge.
You mean it? Oh, sorry. Sorry, babe.
That's how our solar system is going to end.
Sorry, go ahead.
Our solar system is going to end in 5 billion years. Our sun will inflate and become a red giant. What's going to happen is it's going to quit turning hydrogen into helium. And it's going to start converting helium into carbon. And that's a very short-lived phase. When it starts trying to do that, it takes a lot of energy to do that. The sun is going to blow up into a red giant. It'll come out as far as Earth, maybe. It'll incinerate most of the solar system, and that'll be the end. Except we don't have to worry about it because Earth will be uninhabitable by that time anyway. You know why? Because the sun, which started out 30% less powerful than it is now, is getting stronger all the time. So the sun was only 30% as strong when the Earth was first created, but it's 30% stronger now. And it's getting stronger every billion years or so by 10%. So before too long, it's going to be so strong that it will boil away the oceans. So in under 1 billion years, it will boil away the oceans. Once it boils away the oceans, then you won't have any subduction anymore because it takes water to lubricate the subduction. So, first of all, the subduction is going to stop. There'll be no more recycling of carbon. It's going to get hotter and hotter. And the sun's going to boil the oceans away. The electromagnetic field that's around us is going to disappear. Well, what's going to happen is all life on Earth is going to become extinct. I mean, no easy way to say it. So we've got under 1 billion years to get our act together. I figure a few hundred million years, a few hundred good million years, really, right? This is the best time to ever be on Earth. When was the last time you saw an asteroid come flying through the sky? Well, not that long ago, but they weren't really big. Right now, we got 4,000 to 10,000 asteroids a year hitting the Earth. That is, anything bigger than a golf ball is considered an asteroid hitting the Earth. Every 2 centuries, we get one the size of a football field. When we get one the size of a football field, we get, you wouldn't want to be in the immediate vicinity. But that's not nearly as big as the one that landed, that killed the dinosaurs, right? But that was only 10 or 15 kilometers wide. So something the size of Merritt, not much bigger, took out the whole world. It killed all the dinosaurs, one of the most successful species of life that has ever lived, and annihilated just about everything else while it was at it. That was just one 10 to 15 kilometer asteroids. So, but there were a lot more of them in the past. So I can't guarantee one isn't going to show up, but there's none on the horizon right now. So what's the end of our solar system? We're all dead. What's the end of the universe? Well, the universe is expanding, and it's just going to keep on expanding. I just love watching Brian Cox do that on BBC. What's the matter, dear? You look distressed.
No.
I know. I'm not getting very far, am I?
No.
I'm not doing well at all. I'm sorry. Okay, well, forget that. There's your Mid-Atlantic Ridge. Okay, just a sec. Where's my there it is. Hooey. See, I hate getting distracted like this, but everything is so interesting that's what does me in. You know, that's what's so frustrating because I want to be straight ahead like a laser, right? Nothing is going to distract me. And I look at something, and anyway, this is the Mid-Atlantic Ridge. And then what's happening is magma is coming up from deep down in the mantle, and it's going this way, it's going that way. So it's forcing the ocean apart. And it's doing that all the way from there, all the way around. Here's the East Pacific Rise. Goes all around the Earth. It's the longest mountain range in the world, 65,000 kilometers. You can't see any of it. It's all under the water. But that's what's creating all the new land on the Earth. The magma's coming up right along the ridge, and it's going that way, it's going that way. You can even see the lines, even though this is an artist's impression. And it's a good one. And so that's what made the Atlantic Ocean. 60 million years ago, this didn't exist because these two were right up against each other. South America was waged right up against Africa. You can see how they fit together. So 330 million years ago, those were all together. Then Wilson, the Canadian, came along. John Tuzo Wilson came along and said, what's happening is this is being pushed apart here and there. That's creating new land. That caused the continents to go apart. And this is recycling rocks all around the world over and over and over. It's been doing it for 4 billion years. And that's how we get our new land. And that's how Earth controls its temperature. So I just want to make sure that you understand about carbon. That carbon is the central atom for life, even more than oxygen. I mean, and yes, we need oxygen, but we've only lived in an oxygenic world for less than half the time the world has been here. Before that, oxygen wasn't a factor, but carbon was, and as far as I know, always will be. We talked about macromolecules.
Can I just say something?
Yeah.
So if we weren't spewing carbon into the atmosphere, we would.
Oh, yeah. Right at the yeah, thanks, son. According to the Milankovitch cycles, right now we'd be going into another ice age. Not right away, but maybe another 10 or 11,000 years. If all things were equal. So if the Milankovitch cycles were functioning like they used to before any life form was putting a huge amount of CO2 into the atmosphere, then we would gradually be cooling off and going into another ice age, yeah. But we're not. You don't have to worry about it because we're heating the planet a lot faster than that. Heating it faster than we ever have. That's a scientific fact, I'm sorry. It's not politics, it's freaking science. Yeah, so macromolecules, we're going to be talking about those because we're talking about the emergence of life.
Sorry about that.
Oh, yeah! Okay, now, just a second.
You
Okay.
wanted to mention giraffes anyway, so that's
Well,
cool.
yeah, I was going to mention them, but that's a lovely looking molecule.
I know it's
That
gorgeous.
illustrates the fact that molecules are very complex. It illustrates the fact that, I'm just making this up as I go along, but it's true. Not only are they complex, but they also have shapes. And those shapes have to fit together. And that's how proteins work. Proteins, well, all molecules work that way. They have certain shapes, and if they fit together, great. If they don't, well, you're not going to get a chemical reaction. Anyway, yeah, macromolecules, 4 kinds, all right? You got to know them. Proteins, lipids, carbohydrates, and nucleic acids. Proteins, most important. More stuff is made out of proteins than anything else, so you've got to have proteins. What are they? Proteins are made out of amino acids. So you've got your more complex molecule made up of less complex molecules called amino acids. And those less complex molecules are called monomers. Lipids are made up of glycerol and fatty acids, and those are the monomers that make up lipids. carbohydrates are made out of short chains of sugar. When you put the short chains together, they make longer chains. The short chains are monomers, the longer chains are polymers. Finally, nucleic acids, they're what make us us. Nucleic acids, DNA, and RNA. And everything that makes me, me, and you is in the DNA. So we got a bunch of genes in there, and each gene is a section of DNA. And those sections of DNA are made out of little things called nucleobases, which fit together in such a way as to make a bigger molecule. And so this is what a bit of DNA looks like. I'm running out of board here, aren't I?
Do you want a
Okay,
picture?
let's
Do you want a picture of DNA?
Well, yeah, okay. I just want to show you the basic idea, right? So here you got a backbone, and then you've got these bits. You got another backbone and a bit, and the bits are 4 types: guanine, adenine, cytosine, and thymine. And I remember it, all teachers can go. Adenine always pairs with thymine, so this is adenine, this is thymine, and guanine always pairs with cytosine. So here we've got a guanosine, and here we've got a cytosine. And those are the monomers that make up DNA. And there are gazillions of those in us, and as you can imagine, with 4 different nucleobases like that, they can get together in a whole variety of ways. So there's a lot of plasticity in there. There's a lot of flexibility built into it. And the other type of nucleic acid is RNA, so that's DNA. That stands for deoxyribonucleic acid, which sounds big and formidable, but it isn't. All it means is there's a sugar background that's had 1 oxygen taken out, so it's been deoxied, right? Give me that oxygen, I've deoxied it. So it's got deoxyribonucleic acid in the background, and then it's got these 4 little different kinds of bases here. And that's, there's a lot more to it than that, but for now that'll do it. And you've got RNA, and RNA is half of that. It's a backbone, and it's got nucleobases. 3 of them are the same, 1 of them's different. The one that's different is called uracil. So uracil is now going to go with guanine. And basically what your body does is it's got this DNA packaged away in every cell, and that DNA contains instructions for everything that you and I are. Our hair color, our eyes, everything. How we're going to act, what kind of tempers we got, everything that makes us up is in that DNA. But that DNA can't do anything. Okay, it's got all the instructions, but they're just sitting there in the cell not doing something. What the body's got to be able to do is translate that DNA into stuff. And so what it does, so the DNA makes a copy of itself. Then the RNA comes along and grabs that copy and makes a copy of that. So the DNA gets transcribed or gets duplicated into another DNA. That becomes the template that the RNA is going to work with. So the RNA then takes that DNA and it makes a copy of it, except it changes one of those 4 nucleobases. So it has now a uracil instead of whatever the uracil replaced. So the DNA gets copied onto the RNA. Then you've got a type of RNA called messenger RNA. The messenger RNA comes along and it grabs that code, which is what it is, that has been copied now, and it hustles it out of the nucleus into the rest of the cell, and it takes it over to a ribosome, and the ribosome does this thing where it reads it, and then it sends out instructions to another kind of RNA, and this other kind of RNA goes off, and it's been given instructions now, okay? It's been given instructions by this other kind of RNA. This RNA comes along, says, okay, this is what I want. So this other kind of RNA goes off, and it brings back these amino acids, because these amino acids are going to become proteins. And that's how we make proteins. Our DNA says to the RNA, go and assemble according to these instructions. And the RNA runs off, and the messenger RNA and the ribosomal RNA get together, they follow those instructions, and they make proteins out of it. And those proteins make our blood and our muscles and our guts and everything else. And that's how it works in a nutshell. So that's DNA and RNA, and that's why we're going to be talking about that kind of stuff now, and about proteins and carbohydrates and nucleic acids, and that's what they are. Let's see, what else do we have to cover? Oh, okay. Two kinds of particles, right? We got one kind of particle called a boson. We got one kind of particle called a fermion. And we're made up of fermions. They're regular atomic matter. Remember? They start with a quark. Put 3 quarks together, you get a proton. The proton gets together with an electron, and it gives you an atom. The atom gets together with another atom to make a molecule. The molecule gets together with another to make a monomer. The monomers get together and form polymers. The next thing you know, you got a macromolecule like protein. And the protein's made up of amino acids, and the amino acids are put together by the RNA that's running around gathering here and gathering them there and putting them all together, and that's how we get the stuff in our bodies. Okay. Nobody's objecting, right? Passed unanimously. Carrying on. My point then is that there's 2 different kinds of particles. Now I want everybody to know there's 2 different kinds of life. And we're now going to divide life into 2 categories: eukaryotes and prokaryotes. And then, as we go along, the first life we're going to encounter is prokaryotes. That's the simplest kind of life. It's not simple at all. It's very complicated, and it's really a marvel of complexity. But prokaryotes are a lot simpler than eukaryotes. We're eukaryotes. We're big and we're complicated. Each one of our cells has got a real honest-to-God nucleus in it. And in that nucleus is our DNA. And that's why when that DNA is going to be replicated and being made into protein, that's why it's got to be delivered out of the nucleus into the rest of the cell to the ribosomes where it can be assembled. It's read, assembled, the proteins are made, and then we have stuff being made in our bodies. So we just need to know that. Here is a prokaryote. This is the simplest form of life we have on Earth now. All bacteria and all archaea are prokaryotes. But plants, fungi, animals, protists, and us are all eukaryotes. So it was nothing but prokaryotes probably for the first, that's a matter of intense debate. That's one of the things that makes it so hard to present this stuff. The easiest thing in the world would just be to get a text. I'd go through the text and I'd just make up these lessons, and it'd be easy peasy Japanesey, honest to God, because it would all be laid out. The reason I didn't use a text is that you can't get one that's not outdated. The best one I found in this library, and it's an excellent text. If you open it up to about, I was going to bring it along and I forgot, so I'm sorry. But if you open it up to a certain page, it'll show these Ediacaran organisms that lived 550 million years ago, and it's got a great big picture of them, a painting, and they're green. My point is they couldn't have been green, because painting them green shows that the person who painted them thought that they were photosynthesizing. But they couldn't, because it turns out they were found a kilometer down under the ocean, and it's pitch black. Nothing can photosynthesize down there. My point is that even the best books have to be out of date, because we've learned so much in the last 20 years. It's pretty hard to find a book with any information on science that's much newer than about, 15 years old or 10 years old. Even if it's brand new, the information in it is going to be old, because they couldn't get the most up-to-date information in it. So a little bit about the Ediacaran really threw me, and also the fact that according to the same book, there's no such period as the Hadean, because they hadn't even put it together as a real honest-to-God period yet when that book was put out, and that was in 2009. So it's not that long ago. So this whole first period that we're supposed to be talking about right now isn't even in the book, other than they mention it as a possibility. So that's how fast things have changed, and that's why I can't just present to you one easy version, because there's kind of an older version and a newer version. Now we're out of time, and I don't want it to be, because I'm not nearly as far along as I want it to be. I feel I've been a horrible failure because I haven't got to where I wanted.
So you must remind them about an isotope, because it's
Okay.
going to be really important for next time.
Yeah, we're going to be
and
talking
then just
about...
just quickly mention what is life a little bit, couple of minutes, okay?
Yeah, okay. Can you stay for an extra 5 minutes?
Yes.
Okay,
Yeah.
let's do the what is life thing.
Okay.
Or just quickly, I'll finish
But
this
just
off
don't
next
forget
week.
to ask, does everybody remember what an isotope is?
Okay, there are 123 definitions about what is life. I'm not going to worry about it. I'm just going to say that it is that which preserves, furthers, or reinforces existence in the given environment. What are some of its traits? Okay, well, one thing, it's got to be regulate its own internal environment. And we all do this. We shiver or sweat, and we maintain a homeostatic environment. Another thing about life is it's got to find a way to maintain its own identity and keep itself separate from the rest of the universe. That is done by means of cells. All things that are alive live in cells. So you may be thinking, well, what about viruses? They don't. You're right. And viruses are considered not alive for reasons we'll see. Metabolism. If you're alive, you've got a metabolism. And it's all those chemical reactions I talked about. The sum total of all those chemical reactions is your metabolism. What other things? It can grow. Okay, you think that's pretty self-evident, right? Well, let's take a look at those salt crystals.
What number is it?
I got 119. Let me show you something that grows and isn't alive. It's these. These are the world's largest crystals. The longest one is 39 point something feet, weighs 55 tons, and this is deep under the ground, almost 1,000 feet under the ground down in Mexico. And the temperatures down there are about equal to the hottest day ever in Death Valley. So that's why not too many people are down there. But my point is this. Those crystals grow. They started out really tiny, and they got that big. So you can't say it would not be a definition of life to say it grows, because non-living things can grow too. So we've got growth. It has to be able to respond. Okay, I'll end on this note, I think, because we are over time. Okay, so again, my humble apologies for taking so long to get to the point. Okay, I really was trying, and once again I failed. Oh man. Anyway, let's have a look at a sunflower.
Okay. A beautiful-
Because I want to illustrate the point that living things respond to their environment. And the reason that I got Denise to look up a sunflower is that this is just a simple example of how they do it. The interconnectedness of all life shows that we all use the same metabolic reactions. And I'm going to, next week, I'll illustrate two of them for you, photosynthesis and the Krebs cycle, just to give you an idea of how delightfully complex these things are. But I won't go into, I couldn't go into the amount of detail that I'd have to do it properly because it's too complex for me. But I'll break it down so you can get an idea of the complexity but not get too involved in it. Anyway, here we see different life forms.
Sunflower.
Our nictitating,
Sunflower.
okay, I'm just going to try to say
Okay.
that our nictitating membrane evolved when that thing crawled out of the water. That was 375 million years ago. And those are our arms in those front fins. But I want to end up on the sunflowers. If you're alive, you can respond to the environment. How do sunflowers respond to the environment? A sunflower stem has cells growing on both sides of it. It has a thing called auxins, which are hormones. And the sunflower's genes tell the hormones on the shady side of the sunflower to grow faster than the ones on the sunny side of the sunflower. So, in the morning, when the sun is shining from here, the cells on this side of the sunflower are growing faster than the cells on this side, and that is bending the stem. And that's why the sunflower faces the sun. And they continue to, by doing that, the sunflower gets many times more solar radiation than it would have got if it didn't do that. The other thing I gotta tell them about is the giraffes.
Okay.
Okay, all right, so you got a great giraffe picture here.
Yeah.
All right, giraffes evolved with trees called acacia trees. There's the acacia trees, there's the giraffes. So the interaction between giraffes and acacia trees has been going on for a few million years. Because what happened in Africa was back in the day, 3 or 4 million years ago, everything was drying out in Africa. Africa used to be lush, used to be a nice place to live. It was quite green in most places. But about 2,000 years ago, it dried right out. That had been going on for quite a while. Anyway, Africa dried up, and the jungles started to recede, and what was left was a savanna with trees spaced out like this. So the giraffes evolved to munch the trees. what the trees did then, I mean, they're not just going to sit there and take that, right? I mean, life has been an arms race right from the get-go. Make no mistake. It has been the most brutal arms race. If you don't make it, you go extinct, baby. And 99% of everything that's ever been is dead and gone. A lot of it we'll never even know that it existed because we'll never find any fossils, especially if it was little things like bacteria back, because they got nothing to preserve. They don't have teeth. You know? Anyway, the giraffes eat the acacia trees. So the acacia trees develop these great big huge thorns, horrible things. So what did the giraffes do? They evolved big thick lips to eat these thorns. So the acacia trees weren't going to take that lying down, which would be quite a sight. So what they did was they evolved chemical warfare. So the giraffes come along, they start munching the tree, and the tree responds by sending out a chemical message. And the trees pick it up on the breeze, and the trees all start pumping out tannins. And the tannins, it takes a few hours to do this, but the tannins get into the leaves, and the giraffes are eating it. Ugh, it's horrible. But if they're hungry, they keep it up, and the plant keeps pumping out the tannins. And if the giraffe eats enough, it'll get sick. So it finally has to stop. But the giraffes have found a way around that because the plants communicate with the wind. So they send out these molecules float with the wind. The next tree, downwind, it senses it. They got receptors in their leaves, like stomata. And it senses, gets this chemical message, starts pumping out tannins. What if the giraffe walks in the other direction? And that's what they've learned how to do. They graze upwind, into the wind, so that when the plants are releasing these chemicals, it doesn't get affected. Thank you very much. I'll stop on that note, and we're going to continue with What is Life at the beginning next year. So thank you very much.